We are back with the second video for our Unit 3 Day 7 lesson, and in the first example we're asked to determine the solution to this system. So we're given two planes, plane 1 2x plus 2y minus z equals -1, and plane 2 6x plus 6y minus 3z equals -3. And I think probably looking at that we can identify that these are not quite in standard form of our Cartesian equation. So I'm going to take these and rewrite plane 1. I would write as 2x plus 2y minus z plus 1 equals 0. So that's that in standard form. Remember, everything to one side, eliminate any fractions, reduce a common factor, and make sure the first term is positive. So I'm going to do the same to plane 2, and here I get 6x plus 6y minus 3z plus 3 equals 0, and then I know I can reduce by a common factor here. Dividing everything by 3, I get 2x plus 2y minus z plus 1 equals 0. So we can clearly see here that plane 1 and plane 2 are going to be coincident. And again, that's why you need to write the equations of your planes in standard Cartesian form. This is a bit of a trivial solution. You might be given a plane perhaps in vector form and have to put it in Cartesian form to identify that it was in fact the same plane as the other plane that you were given to find the intersection of. But here we can say these planes are the same. Or coincident is the word we use for that. So the solution is 2x plus 2y minus z plus 1 equals 0. So we could come up with and just say any coordinates x, y, and z that satisfy that equation will be part of the solution set for this intersection, which is really any of the points on the plane. Okay. So of course, we do have infinitely many solutions. We can also write this using parametric equations. For instance, if you wanted to come up with an equation to solve for x, y, and z. Sometimes people have kind of a hard time thinking of how to write a Cartesian equation of a plane into a vector equation of a plane or a parametric. And it's actually easier than you likely would think at first, if you haven't come across this yet. So my Cartesian equation of the intersection here was 2x plus 2y minus z plus 1 equals 0. So the normal here is 2, 2, -1. So what we need to find is any vectors. We know the vector equation of the plane is, so we would have a position plus s times one direction vector plus t times another direction vector. So this is what we need to find for the vector equation of our plane. We need a position, which is any point on the plane, and we need two direction vectors. So our position vector, we could find that just by finding any point on the plane, any one at all. I would suggest finding an intercept because I think that that's likely kind of the easiest one to calculate, but you could really sub in any x and any y value and solve for z. Or kind of similarly, you could sub in any two coordinates, x, y, or z, and solve for the third. So what I think is probably the easiest, I'm just going to do up here, is to find the position and just make it the z-intercept. because I have a nice, like, easy to solve for. If I put in x equals 0 and y equals 0, so I have 2 times 0 plus 2 times 0 in brackets minus z plus 1 equals 0, and then that would give me z equals 1. So my position is 0, 0, 1. So that's not too hard to find. For my two direction vectors, I know that the direction vector dot the normal, the direction vectors are all perpendicular to the normal. So we would have any vector that if I gave the dot product with this, it would give me 0. So I'm going to say n dot v1, vector 1, direction vector 1, equals 0, because we know that the normal is perpendicular to all of those. So I'm just going to say 2, 2, negative 1, dot with this one equals 0. And we just need to find numbers to fill in here that would give us some kind of perpendicular vector that would make the dot product equal to 0. So you can really just kind of play around with the x's and y's. You can create an equation and say 2x plus 2y minus z equals 0, and figure out what x, y, and z's would work. I like to pop a 0 in because that kind of makes it a little bit easier. So 2 times 0 is gone. So I just need 2 times y minus 1 times z to equal 0. So what if y was 1? 2 times 1 is 2 minus, and then I would need z to be 2. And just kind of double checking there. That's 0, that's positive 2, that's negative 2. It will equal 0. So that can be one of my direction vectors, and I'll just put it in here, 0, 1, 2. And my other direction vector, I would say the normal dot v2 also equals 0. And again, just kind of playing around with the numbers a little bit. The normal's 2, 2, 1, dot product with something to get a 0. I might put another, I always put a 0 because it makes it way easier. So I might put a 0 there, and then I'm going to have 2 times the x plus 2 times the y would equal 0. So I know if the x was positive, the y would have to be negative. So that's positive 2, minus 2, and 0. So that will add up to 0. And that's my other direction vector. So 1, negative 1, 0. Remember that you have an infinite number of possible choices. All you have to do is find two vectors or create two vectors where if you gave the dot product with the normal, you would get a 0. Once we get this, we can easily write in parametric. So we could say that x is just t, 0 plus 0s plus t. So those zeros kind of come in handy sometimes. Y is 0 plus s minus t, so just s minus t. And z is 1 plus 2s. And no t's because we had a 0 there. So that gives us a pretty clear parametric definition to solve for x, y, and z, if you didn't want to just leave it in the Cartesian equation. So that can come in handy sometimes. As I mentioned in the first video, we can recognize for sure that if the normals are scalar multiples, it'll be either case 2 or case 3. If there's no solution, so if you've put those Cartesian equations into standard form, reduced out the multiples, cleared fractions, made the first term positive, and they're not the same, then it's an easy answer. You just say the Cartesian equations are not equal, so there's no solutions. That parallel case is the easiest one to spot. But if you see those normals as scalar multiples, you know it's case 2 or case 3. If the normals are not collinear, then we know that it's going to be the intersection in a line, or that case 1. So that one is one where we do have to do a little bit more work to solve. So here, we're going to take a look at this one. Actually, this is another a different case. So here we're going to look again, making sure that we get our equations into standard form. So plane 1, 3x minus 4y plus z minus 7 equals 0. And plane 2 is 6x minus 8y plus 2z minus 4 equals 0. And reducing that, we get 3x minus 4y plus z minus 2 equals 0. So we can see that these are parallel. So we can say n1 equals n2. So we've got parallel planes, but this last piece, the minus 7 and the minus 2, are not the same. But the Cartesian equations are not the same, so the planes are parallel. And we have no solutions. The last one, you guys can probably guess that now we're getting into that first case where we actually have to do some solving. So here we can see, I think pretty clearly, we can see that that would be double, but that's definitely not, that's not related. So we're not going to have a parallel normal situation. So we can say right away, n1 does not equal k times n2, so there's a line of intersection. Okay, now this tends to be the hardest one for people to kind of wrap their heads around how to solve. So if we know that there's a line of intersection, I'm just going to kind of build the framework for this line here. So R equals, I'm going to have a position vector and a direction vector for that line. Okay. Now we are going to want to solve for a position vector and a direction vector of the line, but we're going to have to do it using the information that we have in our two given planes. One thing we can do is try to do some elimination, which we've got pretty well set up for that x value. So I might do plane 1 times 2. So then I'll have 8x plus 7y minus 33z equals, oh, I was not multiplying here, 14, I'll have to fix this up before I scan it in, sorry guys, 66, and then equals negative 34. And then plane 2, we'd have negative 8x minus 5y plus 3z equals 7. And then I can add down in these columns to clear out the x's. So I'm going to add to do elimination. So I have 14y and negative 5y. So I have 9y and negative 66z plus 3z. So I have negative 63z equals negative 34 plus 7 is 27. So here we get a relationship between y and z, but we're not going to be able to solve for an x equals y equals z equals point. We're just not going to get that because it's not a point of intersection. What we need to do is solve for x and y in terms of some parameter of z. And I'm going to suggest to you that we take a look over here and we're going to arbitrarily kind of pick some of these pieces of the direct position vector and the direction vector to make our job the easiest. And what I'm going to recommend is that we're going to pick that the position vector has a 0 in the z component and the direction vector has a 1 in the z component. And again, this position vector can be any point on the line. We know that that line is probably going to go through the xy plane where z equals 0. And the direction vector can be any scalar multiple of a vector in the direction of the line. So why don't we just kind of arbitrarily make it the the case where the z value is 0. So what that's going to give us in terms of our parametric equations is z equals t, right? It'll give us 0 plus 1t. So that's going to be very nice and easy to use. Back here, if we know that z equals t, now we can solve for y in terms of t and be able to find those y pieces and then again the x pieces in the next step. So if we knew that z equals t, we've got 9y minus 63t equals 27. So 9y equals 27 plus 63t, and then dividing by 9, we get y equals 3 plus 7t. So now that's our parametric equation for our y. So 3 plus 7t, and then we just need to find the x. So we'll take the y and the z and substitute them into either of the first two equations to solve for x. So I'm going to be a little bit squeezed for space here, but we can do this. I'll go right into the plane 1 equation. So I have 4x plus 7 times the parametric equation for y, 3 plus 7t, minus 33 times the parametric equation for z, which is t, equals negative 17. Again, I'll kind of draw a line to keep that separate. So now I get 4x plus 21 plus 49t minus 33t equals negative 17. 4x equals 49 minus 33, that's 16. So 16t, and if I bring it to the other side, then it will be negative 16t. And I've got negative 17 and then minus 21. So that will give me 38, negative 38. Just kind of skipping a bit of steps here. And then dividing by 4 across the board there, we get x equals, this one won't reduce as well, 19 over 2 minus 4t. So then we can take these and pop them back into the vector equation. So we'd have a 7 and a 3 for the position and the direction of the y, and then we'd have 19 over 2 and a negative 4 for position and direction for our x. So that gives us the parametric and the vector equations of the line of intersection. And again, because there's an infinite number of representations of that line in R3, we're really kind of arbitrarily choosing that z equals t just to make our job easier. You could just as easily choose z equals 17 minus 8t, but it tends to make it a bit more messy to solve. And that's the end of the Unit 3, Day 7 lesson.